And we'll start. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers of the Office of Public Outreach here. If you did not get one on the way in, please grab one on the way out. We have our lithographs here. And tonight's lithograph is the star-forming nebula NGC 3603. A good friend of mine. Yeah, actually, I don't remember anything about 3603. We did the press release on this back in, I don't know how many years ago. So if I wanted to learn about it, what would I do? I'd turn over on the back and I'd read the 350 words we're allowed to put on the back of our lithographs, which will tell you about the stellar evolution that happens when you look into these star-forming clusters, okay? Grab one on your way out if you didn't get one. All right, we have to do this in the electronic age. Silence your phones, turn off their ringtones, and the text notifications, and those camera clicks and everything. Thank you very much. Tonight, our speaker is Nimisha Kumari. Her talk is Cloudy with a Chance of Stars. Sort of a play off Cloudy with a Chance of Meatballs, which would be the NASA meatball, of course, right? All right, it will be about some star formation, which is why I chose NGC 3603 as our thing. Next month, I will be giving the talk on some recent work that we did on the Crab Nebula. We made a beautiful visual, three-dimensional, multi-wavelength visualization of the Crab Nebula, but I will couple that with discussions of supernovae, things that go kaboom in the night. In March, we have Exoplanets, A Search for New Worlds by Nestor Espinosa. And in April, we will have a talk on 30 years of the Hubble Space Telescope. Hubble hits 30 on April 24th, 2020. Yeah, 30 years ago. And the folks who are organizing this have not committed to a single speaker, but they said, oh, we'll probably round robin it. So I just called them an all-star cast from the Space Telescope Science Institute, okay? Let's see. As you all who are here recognize, there is building construction going on. The lobby is being totally redesigned. At least January, February, and March public lectures, you will have to use this side entrance that you used tonight. Everyone found it okay? I put up some signs to make sure it was going. All right. Wow, there's a lot of people here for January. All right, this is great. I mean, I'm not used to an audience being this full in January. Nimisha, you obviously packed them in tonight. So we'll use the entrance, the signs were posted, and if anybody needs wheelchair access, please contact us before. We will do our best to make sure that that is possible, okay? All right. Let's see. Our website, where you can find the list of the upcoming lectures as they go. We have our webcasts here, both on YouTube and our Space Telescope webcast archive. The webcast archive goes back to 2005, back to when it was only Hubble's 15th anniversary. Right around Hubble's 15th anniversary is when we did our first archive webcast. The YouTube playlist goes back about 3 or 4 years or 5 years. If you would like to get emails, wrong one, there we go. If you'd like to get emails, you can sign up right here. Just enter your email address, hit that button, subscribe, and it will add you to the lecture email list. Also on our website are the list of the upcoming lectures. All right, and you've got the various lectures. These are old ones. And for each lecture, if you click down on it, you get all the details, including the abstract of what's going on. They have the view the webcast on the STI webcast, and down here is the webcast on YouTube, okay? So you can use that as a way to find all of the old lectures. Make sure everyone knows the email address. The URL is stsci.edu public-lectures, all right. Email, as I said, sign up at the website, but there are still some people, including one tonight. So I have an email address written right here that I will add to the list tomorrow. I'm quite happy to take analog submissions. If you have comments and questions, you can send them to publiclecture@stsci.edu. Our social media for Hubble, the James Webb Space Telescope, and for STSCI as an entity are available: Facebook, Twitter, YouTube, and Instagram. Myself, I do a little bit of work on Facebook and Twitter. All right. The observatory is not going to be open tonight. I think you might have noticed as you were coming in that it's not a clear night tonight. But you can go to this website, md.spacegrant.org, and you'll find this page of the Maryland Space Grant Observatory open houses. And right here it has the observatory status. And every Friday, after 5 p.m., they will have that updated as to whether they are opening, and you can come look through the telescope then. All right. And now our news from the universe for January 2020. Our first story tonight comes from the American Astronomical Society meeting that was held last week. The reason why we're here on the second Tuesday tonight is because the AAS meeting was last week, and a good portion of folks, including myself, were there at the meeting. At the meeting, we talked about a gentle giant galaxy. All right, so let's start with the Virgo cluster. This is the largest cluster of galaxies in the nearby universe. And actually, this isn't the whole Virgo cluster. This is just the core of the Virgo cluster. Virgo totally contains about 2,000 galaxies. I mean, it's just a massive, this is New York City of galaxies, okay? The galaxies are congregating in this metropolis, all right? And we did a survey at one time looking at the galaxies and trying to and then we put out this image here, which had all the galaxies, about 100 galaxies in the Virgo cluster put on the same scale on the same image. Now, what do you notice about the largest galaxies? The largest galaxies that are up here at the top row, okay, they tend to be elliptical galaxies, right? And matter of fact, there is a category of elliptical galaxies called giant ellipticals. Kind of says, hey, they're kind of big. Has anyone ever heard of a category called giant spirals? No, actually, we don't have a category called giant spirals. I did see in a press release, super spirals, right? But that was a press release nomenclature. I don't think it's official science nomenclature. So our largest galaxies tend to be ellipticals. Except at the AAS, we released this image. Everyone say ooh. And over here you guys say ah. Thank you. All right. This is Rubin's galaxy, or nicknamed Rubin's galaxy. It's actually called UGC 2885. Rubin is a honor to Vera Rubin, who used this galaxy to help uncover dark matter in the universe. Okay, Vera Rubin basically looked at galaxies' rotation and their mass and the visible mass, and deduced that, hey, there's a lot of matter that's not emitting light. We called it dark. Yeah, we're very inventive. All right, now what makes this galaxy special is this is what would qualify as a giant spiral. Okay, you can't tell by looking at it, right? Because it's a spiral galaxy. So I did a little work in my photo editing program today, and to a true comparison to the largest galaxy in the local group, the Andromeda galaxy, looks like that. So up here, this is the size of Andromeda. All right, it's around at least 120,000 light years across. And here is Rubin's galaxy, much, much bigger. All right, and this they called a gentle giant galaxy. All right, why would it have to be gentle? All right, because spiral disks are fragile. Okay, if you get more than 10% of the mass accreting onto it in an impulsive event, those disks flop and warp, and they go all over the place. You lose that beautiful disk. You've got a beautiful disk still here. So this had to inform this large at a spiral, had to have formed in a relatively quiescent way, very, very calm and cool formation, okay? Out in the middle of nowhere, just slowly accreting stuff, becoming one in what I'm told is the largest spiral galaxy in the nearby universe. Okay, this is one of the largest, or the largest spiral galaxy that we know of. Okay, it's about 2.5 times larger in diameter than our Milky Way, and the press release says it contains 10 times as many stars as our galaxy. So we thought our galaxy was big. No, no, This is a big galaxy, okay? All right. Our second story is also from the AAS, although it wasn't a press release of the AAS. It was just a session I attended at the AAS meeting. And it's the shape of KBO 2014 MU69. Although, actually, that's wrong. We no longer call it KBO 2014 MU69. For the flyby last year, they had a press release name, and the press release name was the shape of Ultima Thule. Yeah, they ran a contest to nickname it, and that was what they came up with, Ultima Thule. Actually, but they no longer call it that either. Ultima Thule is gone, and they've actually given, the IAU has finally given it an official name, and so the story really is the shape of Arakoth. Okay, that sounds like it's from Lord of the Rings, doesn't it? Okay, that's actually a Native American word I think I'm given, but it does sound like Lord of the Rings to me. All right, so what am I talking about? I'm talking about the New Horizons mission, okay? And New Horizons originally went past Jupiter and then went on out and visited Pluto, the Pluto-Charon system, okay? And it went past the Pluto-Charon system in 2015. And it was successful. Everything was working great. Whoops, wrong button. Everything was working great, so they said, hey, is there more we can do with it? So they went out and using Hubble, they searched and found a target for it that it might be able to fly, might be able to deviate the course and fly past. And so they got NASA to fund the extended mission, which was to fly past this Kuiper Belt object 2014 MU69. Okay? And they did. And here is the movie of approaching 2014 MU69, which is now called Arakoth. All right? And you can't tell what we're approaching yet. And you'll see as it starts to change. There we go. Now you see the object that we're approaching. Yeah, this is combined from all the LORRI images over time, flying past that Kuiper Belt object there. All right, so this is the high-resolution image of Arakoth, all right? And it is obviously what we call a contact binary, all right? It's two ice balls that slowly came together and merged into one. Does anybody remember Comet Rubber Ducky? Comet Churyumov-Gerasimenko P67 Churyumov CG. Anyways, that was a contact binary, okay? I called it Comet Rubber Ducky because it looked like a rubber duck. Okay, this would be, you know, if it were a comet, it'd be Comet Snowman. But this is KBO Snowman, okay? So it's sort of a two-balled snowman, right? But let me actually go into a little bit more detail, okay? So here is that approach when you're looking at on repeat, and you're looking at it. And it goes from fuzzy to clear, all right? And we're going to watch this approach again. Now we're going to scale it to the same size in every frame, okay? We've got a rotating snowman like this, okay? It's rotating almost in the plane perpendicular to the approach vector. That's kind of cool, all right? But what's really cool is when you look at it, it's got an interesting shape. These are not snowballs. They're actually snow disks. Okay, so this one here on the right, the large lobe, okay, and this is the small lobe. By the way, in the small lobe, this indentation here, that's Maryland Crater. Okay, because JHU Applied Physics Laboratory is where this is being run from, and they named it Maryland Crater. Okay, and so this one, on the right, the large lobe is a relatively flattened disk, about 3-to-1 axis ratio, and the small lobe on the left is about a 2-to-1 axis ratio. And to see that, here is an animation of those two lobes, where the red arrow represents the rotation axis. Isn't this a weird-looking thing? You know? I mean, first of all, you get disc-shaped things, all right? We're used to more potato-shaped things in terms of our asteroids and our comets stuff. And this is two disc-shaped things sort of slammed together, all right? And you can see that the structure is quite interesting. And matter of fact, you look at it and you say, well, wait a minute, how does two disks get together and spin around a central axis like that? That's kind of weird. And you start puzzling through it and puzzling through it. And at a session that I attended in the AAS, they explained some of this, all right? So here is the diagram of the idea of the formation of Arrokoth. So you have your normal formation here on the left, okay? And things are just all agglomerating, all right? And you get to the point where you've got this large object here in the center, the large object, and this more rounded object orbiting around each other around a central axis, okay? And then here in the right panel, they have them cojoined, okay? That they slowly in-spiral in together and gently merge. Okay, remember these are ices, okay? They're not rocks. These are ices that you're packing two snowballs together, okay? But they're continuing to rotate. And like our first story about that giant galaxy that had to live basically a quiet life, all right? This has to also live a very quiet life, all right? Any major impacting strange stuff going on, and this is not going to end up like this. You're not going to get this wonderful, rotation around the axis like that, all right? And so this shows that Arrokoth is relatively pristine, that it hasn't had major impacts and such for about 4.5 billion years, okay? So the folks are really studying the surface materials and whatever they can glean from the flyby, because this is a relatively pristine object from the early solar system. If you look at all, like the moon, right? It's got tons of things smashed into it. It's not pristine from the early solar system, okay? This one is more pristine than any other object that I know of that we've studied, that we had a nice close flyby. We have a question here. What is the size? What is the size of it? I should know that. And matter of fact, I did know that last week. I had it in my notes on my iPad, but I don't remember. It's not tens of kilometers. It's like 5 kilometers for the large object and 3 kilometers for the small object. I can't quite remember exactly, but it is an order of kilometers, not tens of kilometers. Yes, question over there. Ices, yes, and mostly water ice, but also carbon dioxide ice and ammonia ice. Water, carbon dioxide, and ammonia are the major constituents, easy to form molecules that you get. So yeah, but it's mostly water ice. So it's out at the edge of the solar system, beyond it's out in the Kuiper belt, okay, beyond what we call the ice line, where the ices form. Any other questions? Great. Let's move on to our featured speaker tonight. All right, let's switch over. Wonderful. All right, ladies and gentlemen, our speaker tonight is Nimisha Kumari. She only joined us 3 months ago, and she's already giving a public lecture. That's a really great thing from my point of view. She actually is a heavily traveled astronomer, having gotten her undergraduate degree in India, her master's degree in France, her PhD in England, and then came here to the United States. So she said you've done 4 countries in 10 years. Okay, so for an astronomer, that's quite the travel astronomer. Ladies and gentlemen, Nimisha Kumari.
So, hi everybody. So I'm Nimisha Kumari. I'm working here at the Space Telescope Science Institute. I welcome you all. Thank you all for coming. I welcome especially the astro scholars. Could you please raise your hands? Yeah. So they are top students from the colleges in science and engineering, and they are the future of space astronomy. So could you please give a big round of applause for them? Okay, great. So, cloudy with a chance of meatballs. Have you watched this movie or read this book? No. Okay, so So for the people who have, I'm sorry, actually this light is on my eye. Okay, eyes. Okay, I will. So for those of you who don't know about this book or the movie, briefly, in this story, food form in the clouds in the sky, and they fall from the sky. Okay, that is the story. Yeah, that's the story. But actually, I don't know any story about food forming, like the real story, I mean. I don't know any of those stories where food form in clouds and fall from the sky. But we do have evidence of stars forming in gas clouds. So that's why the title of my talk is Cloudy with a Chance of Not Meatballs, but Stars. Okay, so where do we see stars? Space, sky, yeah. And exactly where in sky? Where are they located? Where are the stars? Everywhere. Actually, what you see here, like when you see in the sky, that's whatever stars you are seeing, they are in the Milky Way. That is our galaxy. So stars are actually found in galaxies, okay? And what are galaxies? So galaxies are composed of stars and gas, dust, and they are held together by the force of gravitational attraction. Okay, so this figure here, this image is taken by Hubble Space Telescope over a period of 6 months. This whole strip the image is around, it's actually less than 1 millimeter by 1 millimeter piece of paper held at a distance of 1 meter away, okay? And in this small strip, actually, it's actually a 1/13 millionth of the total area of the sky. And there, you see around 10,000 galaxies, okay? So I really find it very amazing that in such a small area of sky, you can see 10,000 galaxies. Now, actually, Frank already mentioned this. There are various types of galaxies, okay? They are morphologically different. Their physical properties, their chemical properties, they are different. And here on this diagram, actually, it is a way to classify different types of galaxies. This was devised by Edwin Hubble, in whose honor we have Hubble Space Telescope. And in this diagram, different galaxies are located on the handle and on the bars of the tuning fork, okay? There are elliptical galaxies which are on the handle. They are like massive elliptical, their shapes are elliptical. And there are spiral galaxies where you can see spirals. Some of them have got bars in them, and some of them, they don't have bars. And there are some galaxies which are intermediate between the barred and unbarred galaxies, which are kind of represented here. And then there are some other types of galaxies which are irregular. They don't have any proper size. Not size, I mean shape. Actually, they do have size, proper size. But yeah, I mean, so these irregular galaxies, they are neither elliptical, they are not like spirals with arms. They can have bars, it's not necessary that they have bars. So these are irregular galaxies. So if you go on this link, then you will find this picture. And if you click on each of these boxes, then you can get information about each of those galaxies. So I encourage you to go on that link and explore these galaxies. Now, this is the zoomed-in view of some of the spiral galaxies. Spiral galaxies are the most abundant in the nearby universe. For example, the Milky Way is a spiral galaxy. And here are some of the examples of dwarf galaxies. Actually, they are blue compact dwarf galaxies. They are the special class of dwarf galaxies. And those galaxies fall in the category of irregular galaxies, which don't have any particular shape, like ellipticals or spirals. And these galaxies are actually very tiny compared to the spiral galaxies. For example, I have worked on dwarf galaxies, which are about 10% the size of our Milky Way. Now, home sweet home, the Milky Way. You might identify this picture. Actually, this belt is that of the Milky Way, actually. And that was taken from South Pacific paradise of Mangaya, southerly of Cook Islands. So this is our Milky Way, and these dark patches, they are actually dusty regions within our galaxy. And here are images of our own galaxy, the Milky Way, taken at different wavelength bands, so radio continuum, atomic hydrogen. So that is, the wavelength bands go from, for example, from radio waves to gamma rays, and each of these wavelength bands are probing a particular property of the galaxy. For example, this one, the second strip here, which you see, that image is taken in radio, and this image is actually telling you about the atomic gas content of the Milky Way. Now, if we come here, infrared, it's glowing very brightly in the center, and that is actually tracing the dust content of the Milky Way. And for example, the optical, to which our eyes are susceptible, what we see mostly here is dark, actually. There is so much of dust. So the optical light is actually absorbed by all the dusty regions in our Milky Way. Okay? So by looking at an object or a source in different wavelength bands, we're actually looking at different properties of that system. Okay? Now let's look at a zoomed-in view of our own Milky Way. Oops. Okay, so what we saw there was we zoomed into our Milky Way, and then we went into the constellation of Orion. And actually, that is my favorite constellation because it looks like a hunter. Oops, sorry. And I really like this constellation for some reason. These three stars, Betelgeuse, Saiph, and Rigel, they are the three prominent stars in this constellation. And then in the center here as well, on the belt of Orion, there are again three stars. If we go down the belt, on the sword, there is this Orion Nebula. You might have heard about Orion Nebula. This is actually one of the brightest star-forming region, and which is visible to the naked eye. So if we zoom into the Orion Nebula, this is an image which consists of about 1 billion pixels, and it contains about 3,000 stars. So this is around 24 light years across, and it is 1,500 light years away, but still it is visible to the naked eye. So let's see that video again to understand what I just explained here. So Orion Nebula is a star-forming region, okay? And like Orion Nebula, there are several star-forming regions in our galaxy and also in the outer galaxies. So Rosetta Nebula is one of such star-forming regions. So when I'm speaking of star-forming regions, I mentioned nebula. So why does nebula appear all the time in the name of star-forming regions? Can someone guess? Sorry?
Pressure?
So nebula, does someone speak Spanish? Nebula means cloud.
Is nebulas.
Yeah.
Not nebula, but nebulas.
Yeah. So nebula means clouds, and since stars form in gas clouds, that's why star-forming regions are often called nebulas, okay? And this Rosetta Nebula, can you guess why it is called Rosetta Nebula? It looks like rose, okay? And the petals of the rose, actually, these are the reasons where the stars are forming. So this Rosetta Nebula is 100 light years across, so it is larger than the Orion Nebula, and it's 5,000 light years away. So it's farther than the Orion Nebula. So the question is, how do stars form? Let's get to that point. So what astronomy students are taught in school? Well, in grad school, maybe. So what they are taught is that stars are formed in giant interstellar clouds of gas, okay? So to demonstrate that, actually what happens, how stars form, let us assume that, oops, the air is coming out actually, so I need to, okay. So let us assume that this is a star-forming region, okay? So there is gas inside it, which is holding this balloon. So that is like a star-forming region, actually. There is gas inside it, there is gas pressure, and after that, there is this gravitational attraction around it in the star-forming region. What happens, for example, in this balloon is that if I go on pumping air, what will happen? Well, let me try to, okay. If I go on pumping air, let's assume that I pumped a lot of air inside it. What will happen? What will happen is that it will burst, okay? However, if the gas pressure is not that high, what will happen? It will collapse. That happened very quickly. Okay, so the same thing, the same scenario is for a star-forming region as well. There is a star-forming region, there is gas pressure inside it, and there is this gravitational attraction from the outer part, if it is a gas cloud, like it's in the very simple picture of gas cloud. And if the gas pressure is very high, then everything will be blown away. However, if the gravitational attraction is higher than the gas pressure, then the gas will collapse, and that will lead to the formation of stars. But that will happen only for a mass of, for a gas cloud of mass of a particular, which is above a particular mass that is called Jeans mass. Because it was devised by James Jeans. He was a British astrophysicist. So for estimating that mass, there are two parameters which become very important. Those are density and temperature. So the temperature should be very low, and the density should be very high for the cloud collapse to take place. Okay? So here are the subsequent steps of star formation. What happens is that in a gas cloud, different regions have different densities. So when the gravitation dominates, regions of high density becomes even more denser, which leads to the fragmentation of gas clouds, which lead to the formation of cores. And within those cores, stars form. within each core, there can be a single star, binary star, or there can be multiple stars. And those stars they can be very different. Like you might know, like there was a lecture in December here where my colleague talked about different types of stars, but that is for another lecture. So the thing is, fragmentation happens, which lead to the formation of cores, and within those cores, stars form. And then here, for example, again, there is this Rosetta Nebula where you already see those stars forming, or the stars which have already formed. So now you would say, okay, we know how stars form. Actually, we know that that is gravitation, which is very important for the formation of stars. It's the gas cloud where the stars form. So what is it which we don't know? What are we working on? Why are scientists working on star formation? So the thing is, there are many, many things which we don't know. For example, we don't know how gas clouds are formed. Then we don't know what type of gas is actually responsible for the formation of stars. And then the critical process, what is the main driver for the formation of stars? If that process is local or if it is global. By local, I mean if it is just a star-forming region which is important, or if it is a global process, I mean where the whole galaxy, the movements in the whole galaxy leads to the formation of gas clouds, which lead to the formation of stars. If it is a step-by-step process, or everything is happening at the same time. So it's a very complicated thing. We don't know a lot of things. But in summary, what I'm trying to say is that there is no predictive theory. Even though we know that stars form from gas, we don't know if, for example, I have a certain amount of gas, how many stars I will form. That is a question. We don't know how to do that. So you might have heard of Fred Coveley. No? Okay. He's the guy here in the center. Fred Coveley was the founder of Coveley Foundation, and Coveley Foundation awards Coveley Prizes every 2 years. The first Coveley Prize in astrophysics was given to these two astronomers, Martin Smith and Donald Lynden Bell. Their work was on quasars, which was rewarded for during this Coveley Prize. However, like most of the astronomers, they didn't only work on quasars. They worked on many different things. For example, Martin Smith, he worked on star formation. So let's go back to 1959. In 1959, Martin Smith gave a relation between the volume densities of star formation rate and gas. However, measuring volume density is a very difficult thing. Can you guess why? Because when astronomers take data, they are actually images. They are two-dimensional surfaces. To estimate volume densities, we need a third dimension. Okay? So since we don't have third dimension, it becomes very difficult to measure the volume density when we are doing any analysis with the data. So Martin Smith was very smart. He simplified everything. He changed volume density to surface density. So that was his relation. This is, on the left-hand side, you have star formation rate, surface density, and on the right-hand side, you have the surface density of gas. And here you see this n, raised to the power n. And because of this power n, this relation is called power law. And many astronomers around the world, they are working to find out what's the value of n. Okay. So at least here, by looking at this equation, we know that there are two quantities which are very important, star formation rate and gas. And we need to measure these two things before we infer anything about the star formation rate. Okay? So the first thing is, how do we measure star formation rate and gas content. Because once we are able to measure the star formation rate and gas, then it is very easy to measure the density, because then you just have to divide that star formation rate or gas with the area of that region, okay? And that will give you the surface density. So how do we measure the star formation rate? So there are several ways to measure this, but I'm going to, and it is a very active area of research in itself. I'm going to give a very simplified picture here. When we observe anything, any source, any star-forming region, any galaxy, then we do it at a particular wavelength. That can be optical, infrared, radio, like the images I showed you earlier. And why we observe in different wavelength bands is because when we observe at a particular band, then at a particular wavelength, then we are probing a certain property of that region. So we take images, for example. For example, this one is the Orion Nebula in the Milky Way, which I already showed you earlier. And this one is the Whirlpool Galaxy. You might already know that these pink regions on the spiral arms of Whirlpool Galaxy, they are actually the star-forming regions. And these dark patches here, those are, do you know? Dust, yes. Those are dusty regions. So if we want to understand what a star-forming region looks like or how we want to measure the star formation rate, we first need to understand how a star-forming region looks like, what wavelengths we can use to study that region. So let's have a look at a typical star-forming region. In a typical star-forming region, there are stars, which emit, and they are hot and massive stars, and they emit mostly in ultraviolet. That ultraviolet radiation ionizes the gas around them, around the stars, and that ionized gas emits an optical. So from the simple picture of a typical star-forming region, there are two wavelength bands we know would be useful to probe a star-forming region and to understand what is the star formation rate. So those bands are ultraviolet and optical, okay? Now, beside stars and gas, what do you think is present in a star-forming region? Dust. Dust. So this, again, I'm showing you how prominent dust is. For example, here is the Trifid Nebula. And you know why it is called Trifid? Because there are these three lanes of dust. And this Trifid Nebula is actually illuminated by one single massive star here. And this is the dusty lane. That's why it's called Trifid Nebula. It's all because of the dust that it gets its name. And then after that, there is this galaxy, NGC 891. I have put this galaxy particularly here because it's very interesting. It's an edge-on galaxy. So either you can see a galaxy like this or it's like at different orientation, okay? Here we are seeing an edge-on galaxy. And here, perpendicular to this disk of the galaxy, you can see the dust lanes. So dust is actually a big problem. So when we measure star formation rate, the first problem is dust. What dust does is it absorbs the optical light or the ultraviolet light, and when we are measuring or when we are observing a star-forming region or a galaxy in optical or ultraviolet light, then we are not actually measuring all light which is emitted by the star or from the ionized gas, because some of it is obscured by the dust. So what we need to do is observe this star-forming region at a wavelength which can actually trace the light which is obscured by the dust. And do you know which wavelength band would be useful for that? Infrared. Yeah, so infrared is useful for tracing the presence of dust in a star-forming region. Now, let's come to the second problem. So this second problem, people who are working on star formation, not everybody is very much concerned about this problem, but actually it is a problem. I will explain it to you in a bit. So for example, when we have to measure the star formation rate, it's like measuring the birth rate of the world or the birth rate at a region, at a place in the world. So when we are measuring the birth rate, we have to count the number of children who are born, like the younger generation, okay? That's how you get the birth rate. But in the world or in a place, there are not only children, there are older people as well. So to understand the birth rate, you have to separate the babies from the older people. And that's the same case with a typical star-forming region. There are not only young stars, but there are also older stars. So we need to separate the light. Okay, I will say we need to separate the young stars from the old stars, and then that will correspond to separating the light, which is emitted by the younger stars and the older stars. Now, in a star-forming region, you have stars, and you also have dust. Now, dust grains can also be old and young. They can be hot and cold. So they have different properties as well. So not all the dust grains correspond to the current star formation. They correspond to the older star formation as well. So we have to, again, separate that component of dust which is not related to the current star formation. And that also means separating the light. How are we going to separate the light? But the problem is, okay, we have to separate it, and not everybody is thinking. And what the diffuse background. So all this light, which is not related to the current star formation, I call it diffuse background, okay? And we have to separate that thing. And in one of my works, I used a software where I separated these, the younger star-forming regions from the diffuse background. So for example, here, there is this one galaxy, NGC 0628, one of the galaxies in my sample. These are the original images taken in far ultraviolet, optical, and infrared. Now that software was applied, and this middle panel, it potentially contains the star-forming regions which corresponds to only the current star formation, okay? And here is the old unrelated diffuse stuff. So why it is called diffuse? Also because it looks very diffuse here. So that is one of the reasons it's called diffuse background. So now, how do we apply everything, and how we can improve the works, because I'm talking about a work that was that started in 1959. Now, in 1998, Rob Kennicott, he assembled data of 100 galaxies, and then, so what he assembled was star formation rate density and gas surface density. And then he made a plot where there is star formation rate density and gas surface density, and he estimated the value of n. Now, I told you, not everybody works on the same thing. But yeah, a lot of people in the world are working on finding the value of n, okay? So why everybody is doing that if he already did it? The thing is, in 1998, the instruments which we had were not that powerful enough that they could go into much detail. So what he had assembled were the star formation rate density and gas density of entire galaxies, and not the star forming regions. Okay? Now, for example, this is one of the galaxies I showed you earlier, NGC 0628. Here, what we see is that there are several star-forming regions. There is gas, dust, and it's not uniform. It's like the population in the world. There are certain regions where the population is very high. There are certain regions where the population is very low. So if, for example, for the entire galaxy, I assign just one value of star formation rate density and one value of gas surface density, that's actually a very big approximation, and it should not be done. Well, it can be done because it solved a lot of our questions, but then to understand how stars form, we should actually see what is happening at the scales of star-forming regions. So this is the same plot which I showed you earlier, star formation rate density, gas surface density, and here on this plot, actually, each point was a galaxy. I generated several of such plots where each data point was not a galaxy, but it was a star-forming region. And not only me, there are several people working on such things because we have such technologies available now which allow us to probe star-forming regions. So what I meant by replacing each galaxy with several of star-forming regions is this. Here is again this galaxy NGC 0628. The whole galaxy is, for example, this red circle. The galaxy is about 60,000 light years across. I find several star-forming regions there. And the dimension of that is around 1,500 light years. If you compare the two, this dimension is about 40 times smaller. And the thing is, with technologies which we have available now, we can actually do, for such galaxies, 4,000 times smaller. Okay? So I have studied those things as well, but in a different context. So that's very interesting. We use this thing, and then before going any further, I would also like to show you, show you the approach to solve the problem of dust attenuation. Okay, so NGC 0628, the same galaxy which I have been showing you for quite some time, they are in the 3 different wavelength bands: optical, far ultraviolet, infrared. So can someone tell me what optical was for? It was for ionized gas. Okay, dust was infrared, and far ultraviolet was stars. Okay, so we have images of the same galaxy in 3 different wavelength bands. And why do we want to do that? Because then we are measuring different components of a star-forming region or a galaxy. Now, we want to combine actually optical and infrared, because then we will be able to get back the light which was absorbed by the dust, and then we have the complete picture of a star-forming region. We have the light emitted from the stars, and also that was obscured by the dust, and then we use a conversion factor and estimate star formation rate. So that is how we measure star formation rate, taking into account of dust and removing a diffuse background. Now, till now, I had been talking about star formation rate. But in this equation, which I showed you earlier, there was the star formation rate density, and there was this gas density. So what about gas? Which gas forms stars? So this is a very big topic in itself. Which gas forms stars? How do we measure the gas content of galaxies? So if we look at the typical star-forming region again, we have this gas here, And this gas can be present in different forms. It can be ionized, or it can be neutral, the neutral gas, and it can be hot, it can be warm, it can be cold, and it is thought that stars form in neutral gas, cold neutral gas, and the cold neutral gas can be present in two different forms. They can be atomic and molecular. And the most abundant atom in the universe is hydrogen. And it is observed at 21 centimeter or 1420 megahertz. And the most abundant molecule in the universe is hydrogen molecule. But the problem is that hydrogen molecule does not emit much of the radiation, so it's very difficult to measure the molecular gas itself. So what we do is we use different kinds of proxies. So those proxies are like carbon monoxide or hydrogen cyanide. There are several other molecules as well. But when we use these proxies, there are several factors which come in, for example, the metal content. And so that is also an active area of research. So now, going back to 1959, what Martin Smith did, when he gave this Smith's relation of between star formation rate and gas, he actually considered the total gas. Total gas means atomic gas and molecular gas. Fast forward in 1998, when Rob Kennicott studied Smith's relation for entire galaxies, he also found that it is the total gas, that is the combination of atomic and molecular gas, which leads to the formation of stars. So, but at local scales, we don't know what happens. For example, here is the atomic gas map and the molecular gas map of the same galaxy. Now you would say, what is happening here? Why have I put a smaller picture here? Does someone know? Yeah, actually, it's towards the middle. So what happens is that atomic gas is spread all over the galaxy, but molecular gas is just found in the center. So now, I'm showing again the atomic gas map, molecular gas map, and let's compare that with the total star formation rate. Here, the lighter shades, that is lower intensity, and darker shades, higher intensity. If we compare these gas maps with the star formation rate, can you say which gas could be leading to the formation of stars? Molecular gas, right? You can say that right away. But it's a very complicated topic, and not everybody thinks, not even me, thinks that it is the molecular gas which is only related to the star formation rate. Because even the molecular gas is formed from the atomic gas. And many astrophysicists think that there is some other phenomenon which is simultaneously affecting the formation of molecular gas and also the formation of stars. And that could be dust. So this is a evolving topic. People are working on it. And there are several approaches, like further approaches to address these questions. So for example, some of these are listed here. I will go through them one by one. So the first one is, let's investigate other aspects of star formation. So for example, when I showed you a typical star forming region, there was this stars, gas, dust. But to understand what happens, how stars are formed, we have to look at the bigger picture, like in a star-forming galaxy. So stars form from gas, and gas is either accreted in the galaxy or they are formed in situ. Then inside the stars, metals are formed, and then when the stars explode, they are dispersed into the interstellar medium, which is again taken outside or probably redistributed in the galaxy. So if we look at the distribution of the metal content within the galaxies, then we can also infer a lot about the star formation. So how do we measure the metal content? We use a spectroscope. A spectroscope gives us the spectrum shown here of a star-forming region or a galaxy, and there are emission lines which you can use to measure the metal content. Now, the next approach to address those questions is investigating other types of galaxies. For example, the galaxies I showed you earlier, all of those galaxies were dominated by molecular gas in their center. But there are galaxies which are forming stars, but we don't detect molecular gas in them. There are atomic gas. They are dominated by atomic gas. For example, NGC 2403, it is one of such galaxies. And these pink regions are star-forming regions. So it will be interesting to investigate these galaxies and some other galaxies, like these galaxies, the irregular galaxies I mentioned earlier. These galaxies are actually the local analogs of high-redshift galaxies. High-redshift means very distant galaxies, okay? So these galaxies have very high star formation rate, and their metal content is very low. I work on these galaxies, and they are quite exciting to work on because of the upcoming instruments which are focused on the distant galaxies. And then probing even smaller scales. For example, I showed you the spiral galaxy, which is 60,000 light years across. The study was done for 1,500 light years across regions, but the Orion Nebula is 24 light years across. So we need to probe these regions for which we need very powerful instruments. Now let's look at a few instruments which were used in the works I have shown you till now. KPNO, which observes in optical, Galaxy Explorer, which used to observe in ultraviolet, actually, both far ultraviolet and near ultraviolet. Spitzer, which was named after Lyman Spitzer, it was for infrared. IRAM, that is in Spain, that allows us to study the molecular gas content of galaxies. VLA, that allows us to estimate the atomic gas content of galaxies. So I showed you these instruments because they were relevant to the works I had shown you. But there are several other instruments, and the interesting point is that most of these instruments, like all of these instruments, they are either photometric. They can do either photometry, that is take images, or they can do spectroscopy, that is taking spectra. But now we have this very powerful technology, which is called integral field spectroscopy, which combines the power of the two. That is, you can do photometry and spectroscopy at the same time, and you can measure star formation, gas content, metal content for each pixel in your image. And that is very powerful. Some of these telescopes are instruments are MUSE on Very Large Telescope, WEAVE on William Herschel Telescope, KCWI on Keck, you might have heard of it. And now, JWST. Almost everybody in the world who is interested in astronomy knows about JWST. This is a telescope which would be very useful for me because it has two instruments which can do integral field spectroscopy, I explained just now. And those instruments are NIRSPEC or MIRI, and MIRI, you might have heard about them. So JWST is scheduled to be launched in 2021, and this is going to be the largest telescope in space. So let's have a look at this video, why this telescope is so important for all of us. Oh, sorry. Okay, so I hope you liked the video. There is this last thing, last thing about an opportunity happening here in Space Telescope Science Institute in summer. It's the Space Astronomy Summer Program 2020. I was a student in 2013 as a part of this program. You can find me here. I'm here with all of my friends. And now, last year, I joined here in Space Telescope Science Institute as an astronomer. So it is a real great opportunity. So last year in 2019, there were these young students, young summer students who worked on different topics. There were 5 international students. There were also some local students from the University of Maryland and Towson. And this year, 2020, I have proposed 2 projects which are based on data from the IFU instruments, the technology I just explained that combines photometry and spectroscopy, and that those data are from Keck and from Very Large Space Telescope. So I strongly encourage students to apply for this program. Applications are now open. It was a real opportunity for me. I really enjoyed my time, and it was one of the most rewarding experiences of my life. So I really encourage the students. Thank you so much for your time and attention.
Want to handle some questions? Turn my microphone back on. All right, I'm back. All right, we have questions for our speaker. How about right there? We'll start there.
So what is N turning out to be? You look at it with some detail. Can you find regions better value for N here?
So what happens is that when I did my work, the value I got agrees with the value which Rob Kennicott got in 1998, and the value is 1.4.
All right, question over there.
Your model describes
There we
gas.
go. We don't
Your
have our
model
microphone.
describes gas as having expansive qualities, I'll call it. And I don't understand why it isn't simply inertial resistance to collapse. Why is it expansive in any way?
So there are different, well, that's right. So there are different factors which are affecting the formation of stars. When we look at a star-forming region, there is this gravitational collapse, like there is this gravitational force, there is pressure, there is turbulence. There are several different
But the
factors.
pressure you're describing is expansive, is resisting collapse.
Yes.
I don't understand why. Why isn't it just there? And having inertia that's resisting collapse.
So what is it that you don't
I
understand?
don't understand why the word pressure is involved in the description of the gas.
Is he not catching the gas has a temperature to it, and thermal pressure always is going to provide resistance against it. So when you have a gas at a certain temperature, by the ideal gas law, you have a pressure associated with that temperature, and that is going to resist the inward pressure, the inward force due to gravity or other things.
Thanks, Frank. Yeah.
Missing?
Yeah. Thank you, Frank. Yeah.
All right, right behind you, there's a young gentleman who had his hand up.
I was just going to ask if the Betelgeuse star in the Orion constellation is named after the character.
Well, Wikipedia will have the answer for that question, I'm sure.
Everybody wants to know. All right, so the question was?
Betelgeuse.
Oh, yeah, so Americans have, there was this movie with Michael Keaton in it called Beetlejuice. Spelled beetle as in the bug beetle, and juice as in like orange juice. And so many Americans pronounce it as Beetlejuice when it's Betelgeuse.
Oh, okay.
And they sort of think that the movie and yet no, the movie isn't even named after the star. It's a total. It's a transformation of the name into something weird.
Okay.
So yes, you probably, being from India, you may not have seen that movie. Yeah, Michael Keaton was long ago. Yeah, has nothing. The two have nothing to do with each other.
If it helps you remember the name of the star, though, mission accomplished.
It's okay. All right. And by the way, if you haven't heard, Betelgeuse is actually dimming, and we're not sure why. We expect it to start brightening back up this month or next month. And if it doesn't happen this month or next month, something really interesting is going on there, okay? It has some pulsation cycles, and we can sort of explain what's going on right now by some of these pulsation cycles. But if it doesn't change out of this cycle, yeah, kind of interesting. All right.
I'm going to cheat and ask two questions as one question. What exactly is dust, and does it contribute in any way to star formation?
Yes. So what exactly is dust? Dust are, well, there are different types of dust. For example, there are silicate particles or carbonaceous particles. There are polychromatic aromatic hydrocarbons. Those are dust. So dust is made up of different kind of molecules or atoms, grains. So that is dust. And your second question was if it affects the formation of stars. Yeah, so for example, some people also think that dust actually leads to, dust acts as a catalyst for the formation of molecules from atoms. So in that way, that might lead to the formation of stars. So for example, highly star-forming regions, they are highly dusty as well.
Okay, we have a question from online. How strong are the magnetic fields in these molecular clouds? And does that affect star formation, is I guess what the question would be.
Yeah, so there are theoretical works going on about how we can incorporate magnetic fields, like theoretical works actually, mostly theoretical works, to understand the effect of magnetic fields on the formation of stars. So that magnetic field, turbulence, gas pressure, density, gravitational force, all of these factors play an important role in the formation of stars. So, yes.
Okay.
How much gas mass is needed to allow fusion to begin?
Oh, that is,
Star.
so that is exactly what James Jeans did. He gave this recipe. It's called Jeans mass, which is based on density and temperature. And for a given density, so it depends on, it is not only the gas mass, but it also depends on what is the density and what is the temperature. And from this density and temperature, we can estimate the gas mass. So the density and temperature depends on the conditions in the gas cloud.
So there's a related question that people often ask is, so if you have, 1,000 solar mass cloud, how much of that is actually going to form into stars? What percentage of that actually makes it into stars?
Well, I don't really know, but I don't really know. But for example, I can give you here this picture. So here, for example, the gas density. So you said thousands of.
If you had 1,000 or 10,000 solar mass gas cloud, people ask questions with how much of that makes it in stars? Is it 1% or is it 10%?
Yeah, so that is a question related to the efficiency of star formation.
Right.
And efficiency of star formation is very low compared to what is available. Like it is known to be very low, and that is also a question people are trying to understand. Theoretically, for a given amount of gas, the star formation rate should be very high. But for some reason, the efficiency is so low, it's about 1%, 0.01, for example. And here, for example, I was just trying to give you an estimate, but I think it's fine.
Yeah. Okay. Sorry.
Yes, earlier Frank had shown he was talking a little bit about dark matter and how it was inferred by, I guess, the gravitation, to try to explain the rotation of galaxies. And I've heard or read that there's a lot of dark matter out there. Could that not be playing a role, or are you worried you might be missing something by not taking something like that into account?
Well, that might be, but at these scales, I don't think that it matters. So
yeah, it's hard. If you can't measure it, I guess you can't get it into the model. But if there's so much of it out there, it makes you wonder if there's.
Yeah. I mean, like people are working tirelessly on understanding the nature of dark matter, and that when we first understand its nature, I think that will become more easy to incorporate such things in this topic, which is already a bit complicated.
I mean, from a cosmologist's point of view, dark matter is generally considered smoothly distributed on galaxy scales. It can be clumpy on galaxy cluster scales, but it's relatively smooth across an individual galaxy scale. Therefore, it would just be a background field that's relatively smooth, not changing the star formation too much. I'm not a star formation expert, but that's from a cosmologist's point of view. Yeah.
When you say dust, are you talking about like the kind of dust you might see on the street or in a household, or is it more like cigarette smoke?
Well, cigarette smoke, that should contain carbon. So these, the dust particles, they might be molecules, atoms. They can be silicates, carbonaceous particles, polychromatic, aromatic hydrocarbons. So there are different kind of things. And if we look at the amount of dust which is present in the interstellar medium, then we actually won't be able to see each other in this room. So it's so thick. Yeah.
Okay. Other questions? Going once. There we go.
Could adjacent stars' ultraviolet radiation accelerate or impede a transition from atomic gas to molecular gas?
I didn't understand your question, the first part of your question, the adjacent stars?
I think of the ultraviolet as tending to split things apart, but in this case, I'm wondering if maybe the single atoms of the atomic gas are in some way being compelled to join together and become a molecular gas.
Oh, okay, I understand what you're trying to say. Okay, so, okay, actually you are actually going into the direction of feedback. Feedback is another topic we study a lot. Okay, so it's like destroying molecules, or feedback process destroy molecules, and there is this atoms combine to form molecules. So that is a different another topic as well. And those feedback process, for example, if there is supernova explosion or things like that, then it might happen. And these radiation might also break these molecules into atoms. So yes.
Okay, so if we have no more questions, we have one more question.
Just interested in the size of the particles in this dust. No, there must be a range.
So they are grains. So they are angstrom sizes, I can say. Angstrom is 10 to the power minus 10 meters. So and their sizes vary a lot. Yeah.
Thank you.
All right. So if there are no more questions, great. We will see you all again on February 4th, where this guy, Frank Summers, will be speaking on the Crab Nebula and things that go kaboom in the night. I thank you all for coming out on this January evening, and let's give Nimisha one more time.